Hello everyone, welcome to yet another video of electromagnetic field series. So in this video series we are going to discuss about unit 3 of electromagnetic fields, which is magnetostatics. So in magnetostatics we are going to discuss about the basic laws first. So before that, let's recall the topics that are being discussed in the previous classes, which is the electrostatics. So these are the short mind map regarding the previous topic that we have discussed. For today's discussion, we are going to see about the fundamental laws that governs magnetostatics, in which the first and foremost is the Lorentz law of force. And this is the agenda that we're going to follow today for this Lorentz force discussion. So let's get started. First, let's explore the magnetic force in action. Let's have a live demonstration of this magnetic force. You can easily set up this live demonstration at your premises itself. Consider a simple circuit wherein which a wire is placed within a strong magnetic field. So take a magnet, place a conductor or a wire as shown in the figure, and connect a battery to the wire. When we pass an electric current through the wire, we will notice a distinct movement. A movement in the wire is clearly observed. Now, why this wire moves? This demonstration of current carrying wire moving in a magnetic field provides a macroscopic example of the microscopic Lorentz force. So this Lorentz force that is being executed by this individual charge carriers will contribute to the movement of the entire wire. So this entire wire movement is a cumulative result of the magnetic force acting on the individual charge carriers inside it. Now let's get into the Lorentz force. What is the Lorentz force? It is the magnetic force on a single moving charged particle in a magnetic field. So this can be expressed mathematically as F is equal to Q into V cross B, where Q is the charge of the particle and V is the velocity of the charged particle, B is the magnetic flux density or the magnetic field vector, and F is the magnetic force vector. Here the cross represents the vector product, which means that force is always perpendicular to both the velocity of the charge and the magnetic field. And this magnitude of the force F is equal to QVB sin theta gives that theta is the angle between V and B. So using this Lorentz force, we can visualize that the wire moves because of this force. Now, in order to understand this vector nature of velocity and magnetic field, we can apply Lorentz force equation in practical by sketching a practical scenario wherein which a particle is being. So you can easily visualize this magnetic force vectors in a particle entering a uniform field or through the field lines which are very much aligned to the field lines. And then how we can find the direction of this magnetic force? With the help of this right hand rule. This right hand rule is a good rule for determining the direction of magnetic force. So it is very crucial to identify this velocity or this magnetic field through which we can find the magnetic force. But by simply applying right hand rule, we can easily find the direction of the magnetic motion. So now point your fingers, align your fingers in the direction of the as shown in the figure, which shows that the pointing finger represents the velocity and the forefinger represents the magnetic field and the thumb represents the magnetic force. Now, how we can apply this right hand rule in practice? We can visualize this with the help of an electron in a TV screen, wherein which an electron beam that moves horizontally towards the right, through which we can easily detect the electron deflections, because that deflection is a result of this Lorentz force. And also the proton emission in a mass spectrometer wherein which you need to find the direction with the help of this right hand rule, and also the charged particle in space can be found. It's whether their movement can be analyzed with the help of this right hand rule. So now let's have a quick test for the topic that we have discussed in detail right now. First, if the positive charge moves east in a magnetic field pointing north, what is the direction of the force? Immediately apply your right hand rule and find the direction. And how does the direction of the force can change for a negative charge compared to a positive charge under identical conditions? How the sign plays a significant role. And the last one, what is the magnetic field force on a 2 coulomb charge moving at 5 meter per second perpendicular to a 0.5 Tesla magnetic field? So we know the force is equal to F is equal to Q V cross B. So we have 2C here as Q and 5 meter per second as V, and B is equal to 0.5. So by directly applying these values, we can easily get the magnitude of the force. So these are the key takeaways of today's discussions. We have discussed about fundamental interactions of the individual charge carriers because of the current, which is the result of Lorentz force, and we have seen about what is Lorentz force, what is its equation, and how this Lorentz force can be visualized through certain real-time scenarios, and also how we can find the direction of this force using the right hand rule. So for further explorations, you can visit through these websites or links for deeper understanding, and also you can simulate this Lorentz force simulations with the help of some visual experiments. So this is the final question for you to think deeper about this topic, so that you can guess a further clue or further understanding about this Lorentz force. That is why I've given this question. So have a look at it and analyze deep into this topic so that we can have a deeper understanding about Lorentz force. So with this, we have come to the end of this video. We have discussed in detail about what is meant by Lorentz force. So this Lorentz force discussion is based on a DT approach. So therefore, first we empathized, and then we've defined the problem statement, and finally we concluded that the solution for this is Lorentz force, and then we deep dive into the Lorentz force concept. So I hope this video gives a clear insight about Lorentz force, and we will meet in the next video for yet another new law on magnetostatics. Thank you. Thanks for listening.